In this video, we give a formula for the shortest distance between a given line and a given point. So say the line has an equation ax plus by plus c equals 0, and the point has coordinates x0, y0, and what we want to do is find the shortest distance between the point and the line. In other words, the shortest distance between a point and some point on the line. And that formula is that distance is given by the absolute value of you plug in the coordinates of the point into the equation of the line, and then divide by the square root of a squared plus b squared, where a and b are the coefficients on x and y, respectively. So the proof is, well, first notice is that one normal vector to the line is given by the coefficients of on x and y. So that's a and b. So that's a normal vector to the line. Normal, again, is another word for perpendicular. So this vector n will be perpendicular to the line, as illustrated in this picture here. And again, the reason for that is that the equation of a line we discovered by setting the dot product between a vector between 2 points on the line and the normal vector being equal to 0. Okay, then let q be some arbitrary random point on the line, and it's not pictured in this picture, but anyways, let q0 and q1 be the first and second, or x and y coordinates of that point q. And then because the line is given by this equation here, the normal vector dotted with x minus q0, y minus q1 is equal to 0. Then when we simplify this, we get that n is replaced by ab. Expanding out the dot product, a times this term is here, b times this term is here, that's all equal to 0. And so this is the equation of our line in terms of q0 and q1, but we've already known that the equation of a line was given to us like this, and so this forces us to conclude that this term here is equal to c. So we're going to need this result on the next page. Okay, so here's our point P0 that we're given, here's our line, here's the distance we want to find out. Now here's a point Q, random point on the line, and the normal vector originating at Q. And the key idea is that the projection of this vector from Q to P onto the normal vector n is going to equal this distance times the unit normal vector. So we took the normal vector n that we found and divided by its norm, so that this vector has length 1. And that length 1 times d is going to be this length. And so that's therefore the projection of QP onto n. So that's essentially this vector here. Now there is some slight ambiguity of plus and minus. Let's not worry about that too much, but the reason is if the normal vector n happened to be going in this direction, then there would be a negative sign. Okay, so now we use the formula from a previous video of what is a projection of a vector onto another vector. And that formula is you take the dot product of the two vectors and divide by the norm squared of the vector you're projecting onto, multiplied by the vector you're projecting onto. Okay, so then what we get is this term here times this vector n is this scalar multiple of the vector n, and n, let's simplify that, n is equal to a comma b. Q to P0 is P0 minus Q component-wise, so that's done here. And then one copy of n has cancelled from here, so we're just left with one copy of the norm of n. And taking the absolute value will give the value of d. d is a distance, so it's a positive or 0 and number. Okay, and then expanding out the dot product, we get this in the numerator. In the denominator, the definition of a norm is the square root of the sum of the squares of the component vectors. And then doing a little bit of algebra, distributing the a and the b, we get ax0, by0, and then we have this term left over, a times q0, and the b times negative q1, and that's where we use this factor on the previous slide, that this part here is equal to c, and so we have d is equal to these things. I've forgotten the absolute value signs, but they should be there. Okay, let's do a simple example. This says find the distance between the line y equals 2x plus 3 and the point 7 comma 6. And the solution is, well, first we need to express this line in the form given in the theorem. So we need to bring everything to one side of the equation. Here I've sent the y over to that side, or subtracted y from both sides to get this, or I could bring everything to the the side that y originally was on, and I'd get the negative of what I have here. Both would work for the formula. That's why the formula needs these absolute value signs. Okay, and so then the formula says, well, the distance is 2 times the x0 minus y0 plus 3 all over the norm of the coefficient of, well, the vector that's formed by the coefficients of x and y. And so that's 2 squared plus negative 1 squared. That's negative 1 is coming from the coefficient of y. And then we plug in our x0 and y0 for, in this case, they're 7 and 6. Do the arithmetic, and we are left with 11 over square root of 5. And then I want to mention the three-dimensional version of this theorem, which is proved in exactly the same way. The shortest distance between the plane given by this equation and a point in 3 space that has 3 components, x0, y0, z0, is given by the absolute value of, basically you plug in the point into the equation of the plane and then divide by the norm of the normal vector. So that's square root of a squared plus b squared plus c squared.